Good morning, everybody. Hope it's a nice and wonderful day in your neighborhood today. Sure is here. Are you ready to learn some pre-calculus? All right, let's go for it here. Let's quickly go over one of the problems in your homework because some of you guys did not do too well with the graphing tool, so let's figure it out here. All right, so we have to graph this exponential function. So click the graph. All right, so pick the exponential curve. Got it. All right, now put a point somewhere on the graph. Got it. All right, now the key here is you want to identify what the base is, which the base is the number that is underneath the exponent. So in this case, it is 5. Okay. And this 3 out in front, okay, when you are multiplying by 3, it is what we call a stretch, okay, if it's not in parentheses and it's multiplying the whole function by 3, okay. A shift is if you're adding or subtracting. A stretch is if you're multiplying. So we are stretching by 3. And that's going to cause the initial value of the graph to be at 3, okay? That's where it looks like here, okay? That's the initial value of the graph. Now, you could get to the initial value of 3 by vertically shifting the whole graph too, but that's not what we are doing here. So we're going to hit save, hit check, and voila, well done. Okay, domain, that's the possible x values. And guess what? The graph is going from negative infinity, and it actually keeps on going. So it goes all the way, x goes all the way to infinity. So let's get that in there, and voila. All right, the range. All right, now notice the y values. There is no y values that are shaded here, so the range is basically everything from 0 upward, okay? Now, it actually doesn't actually touch 0 because it has a horizontal asymptote at 0, y equals 0. So it's 0 to infinity, the y values go. All right, let's see what's next. Continuity. It is continuous. There is no like vertical asymptotes. Is it increasing or decreasing? Looks like from left to right it is going upward, so that's an increasing function. Is there symmetry? Doesn't look like it. Okay, next question. Is it bounded above? No. Is it bounded below? Yes. It's bounded by the line y equals 0 because that never gets to 0. All right. Does it have any extrema? So that's like where you see the roller coaster hills and valleys. No, there's no roller coaster hills and valleys. All right. Is there horizontal asymptotes? Yes. At y equals 0. Okay. And the vertical asymptotes? No, none of those. Okay. And that is it for this. Oh, wait. Limits. Okay, so as x approaches negative infinity, so I'm looking at this tell, what is y doing? Okay, y is not going down. Y is getting closer and closer and closer to 0. All right. As x goes to infinity, so over here, what is y doing? Y is going through the moon. All right, so y is going to infinity, and there we go. And that is it. I think we're done with that one. Now on to the next lesson. Here it is. And here we are, exponential and logistic modeling. Okay, so in this lesson, you're going to be looking at modeling real life things with these exponential functions. All right. So if it's getting bigger constantly each cycle by the same percentage, that's what we call a growth model. If it's shrinking, decreasing by a certain percentage each cycle, that's what we call a decay model. Each cycle could be a month, it could be a year, it could be a couple hours. So you have to pay attention to what the cycle is. The cycle, most oftentimes, is the exponent on these exponential functions. All right, so in example 2, we have an initial population of 25,000. It's increasing 5% each year. What would be the population after 5 years? So let's look at what it would be if we didn't have exponential modeling. This is what we would have to do. We have 25,000 plus 25,000 times 5% as a decimal, 0.05. All right? So we are adding to 25,000 a certain amount each year. that amount ends up being 1,250. Okay, now you could write that as 25,000 times 1, that's the initial 100%, okay, so to speak, plus 5% more. Okay, so for the second year, you would do 25,000. This is how much you would have after the first year. Plus, here's the increase, okay? 25,000 times the quantity 1 plus 0.05 times 0.05%. So this here represents the increase for the second year. And you could write this as 25,000 times 1 plus 0.05 to the second power, okay? Because you're multiplying the same part twice, essentially. So the increase is actually more for the second year because you have a bigger base population to increase by 5%. The third year would increase even more, okay? And so you could basically the same thing, only it's now to the third power, okay? You're multiplying that 1 plus 0.05 3 times. The fourth year, it's now to the fourth power. Fifth year, now to the fifth power. Okay, so in the end, it's a lot easier to do this rather than doing this all over and over and over again. You'll have about 31,907 people, okay? Exponential modeling there and at its finest. All right. So, if something is increasing with a constant percentage rate r, okay, that was the 5%, and the initial value p sub 0, okay, for t years, we can model an exponential increase as, okay, so this is the P for maybe population after t years is the initial population P sub 0 times the quantity 1 plus R. And R is a rate, and it's almost always written as a decimal, okay, because it's 5%, 5 divided by 100, 0.05. Okay, so you want to make sure that R is written as a decimal. And T is time factor. Could be years, could be months, depends on how quickly it is increasing. So like, is that percentage every year? Is that percentage every week? Percentage every day? All right, so if P sub 0 is greater than 0, okay, so we have a positive initial population. If R is positive, then we will have a growth model, okay? If R is negative, it will become a decay model, okay? It's going to shrink our function, okay? Or if you see 1 minus R, okay, so if we're less than the value of 1, essentially, we're multiplying the initial population by a number less than 1, it would be a decay model. Okay, here's another example. Write a function that satisfies these conditions. You got 52 people, or 52 initially. It's increasing at a rate of 2.3% per day. All right, so boom, there's your function. You got the initial. You have 1 plus 0.023, that's the percentage as a decimal, and you want to make sure to specify what your 0.023, and just simplify this rather than keeping it as an addition. All right, let's go to the next one here. Okay, this question is asking you, is this a decay? What is the constant percentage rate of growth or decay? Well, first, notice inside the parentheses, this is less than 1, so it's showing me that it's a decay. Now you just have to figure out how much less than 1 it is. So take, 1 minus this, and you can figure out how much decay is going on here. They did it a little bit differently. They had 1 plus R equals this, and then they solved that equation, and they show that it became a negative value, which shows that it's a decay value. But anyhow, this is the decay rate. If you move the decimal point, you can make it into a percentage. It is 0.32% rate of decay, okay? Hope that makes sense. All right. So we got this here, and it's showing in a general, an exponential function for growth is 1 plus R to the t power, okay? If it's the growth rate is proportional to the original rate or size, okay? You can also do, instead of 1 plus R, if it's doubling, you could use 2, okay, in place of 1 plus R, or tripling, you could use 3 in place of it. For decay, if it's getting cut in half, you could use a half in place of 1 plus R. That's where you get the idea of half-life. You're putting the rate as a half. Okay, And there are a couple examples of this. Please look at them on these pages, which are correct here. One's about bacterial growth, and the other is about radioactive decay. But let's keep going here because, you don't want to hear me talk about that. All right, so here you have an initial mass of 17 grams. It decreases by half once every 32 hours. Write an exponential function that satisfies these conditions, okay? So we know the initial, it's 17. It's a decay function. So in place of 1 plus r, we're going to put a half, okay, or 0.5. Now the time, okay, so if time represented just hours, then this function would be like way off. It actually represents the number of groups of 32 hours, okay? Well, t here is actually representing hours, okay, but it's decaying every 32 hours, so to represent how many times we have decayed, we have to take our time and divide it by 32, and that shows you how many groups of 32 have actually decayed, have occurred here to shrink down our initial mass, okay? All right, let's look at example 4. We're determining a formula from a table here. Okay, so remember, this is your basic exponential function. We don't know if it's a growth or decay. It really doesn't matter at this point. First thing you want to do is look at your initial value. Your initial value is where x is 0, and you see it's negative 5.8. So you're starting with actually a negative number initially. Next thing you need to determine is your factor of growth or decay. So in order to do that, you just take two consecutive values, okay, two different consecutive x values, and you compare them. Okay, so you take the g of 2, which is negative 3.712, and you make a ratio of it to g of 1, which is negative 4.6.4. That ratio ends up being 0.8. Okay, so in most situations, this would represent a decay here because the value is actually shrinking here, okay? And the growth factor is less than 1. Okay, but if you look at this table, you notice here that these values are actually going up. And that's kind of weird. I'll talk to you about that in a second here. But it doesn't matter which two consecutive values you pick, okay? G of 1 divided by G of 0 is still 0.8, okay? So you just pick two consecutive y values or G of x values and divide those to figure out if your growth or decay factor, okay? So next you just substitute that in, okay? And this actually, like I mentioned, it's a weird growth model because the values are going up even though your factor is less than 1. The reason being is because your coefficient in front of your constant initial value is negative here, okay? And that causes it to basically do a reflection, all right? Most growth values have this being more than 1, but not this particular one because of the negative. It's a y-axis reflection of a decay model, so it kind of flips things up and makes it a little crazy, all right? Anyhow, that's about it, guys. I hope you have a great day. Remember to wash your hands, stay apart from people because, that coronavirus, we got to stop it in its tracks as best as we can. All right. Take care now. God bless you, and hope to speak with you soon. Bye-bye.